Hi, and welcome back. This time we're going to be looking at how reactions occur and relating this back to what we call collision theory, which is a way for us to describe why reactions happen and the criteria that need to be met in order for that reaction to actually happen. So let's get started. Hopefully you'll remember a little bit about the particle model. So the particle model is what we got introduced to even back as far as year 7, where we said that all molecules are made up of particles. And now that we're in year 10, we know that these particles can be atoms, they can also be molecules or compounds. Okay, so in this case, we need to remember that molecules are always in motion, even when they're in a solid, okay, but in a solid, it's vibrations only, okay, and that they are tightly packed together. As we increase the temperature, this solid will melt, forming a liquid. So if you think about this, going from a solid to a liquid is going to be an endothermic process because we need to absorb energy in order to do this, okay? Because then a liquid is going to have a higher energy level than the solid. Okay, and we know this because the particles are going to be moving more, so they have more kinetic energy. And they have no fixed shape. They take the shape of the container they're in. If we add in more energy, we go from a liquid to a gas. Again, we're adding in energy, so this would be an endothermic process. And then the system now has more energy. It's more disordered. We have a greater kinetic energy, and the gas is moving around much faster. Okay, so if we go from a low energy state to a high energy state, we need to absorb energy from the environment to increase that kinetic energy. If we go the other way, if we cool the temperature, okay, we are going to cause condensation, and by cooling it, we're removing energy from the system, putting it out into the surroundings. So this is going to be an exothermic process. Okay, this is going to be an exothermic process that we talked about last time when we go from a gas to a liquid or from a liquid to a solid, because in this case we need to remove energy from the system and put it into our surroundings. Okay, so this is the particle model. So our system has energy, okay, and it is made up of particles that can move around. How this relates back to our chemical reactions is what we call kinetic molecular theory. So this means that the molecules are constantly bumping into each other, okay, but when they bump into them, sometimes they react and sometimes they don't. So this is what we mean by collision theory. So in order for a reaction to occur, there's actually two conditions that need to be filled. The first of which, okay, we know that they have to collide. So in order for a reaction to have a chance of occurring, two particles need to come into contact and bash into each other, like a dodgem. Okay, when they do that, there's two criteria for that collision to know if it will react and form a new product. That is that the molecules must collide with the correct orientation, so they need to be facing the right way for that to occur, and they have to involve a certain amount of energy, the minimum energy, which we call the activation energy of the reaction, okay? Because if you remember, in order for the bonds and reactants to break, we need to put in a certain amount of energy, and that's what we're talking about with our activation energy. If only one of these conditions is met, then there is no reaction, okay? We have to have both met or nothing happens. So let's look at orientation in a little bit more detail. So molecules must collide with the correct orientation, and orientation just means direction. They need to be lined up in the right way. So molecules will move about, particularly gases, in a random way. Okay, so different atoms from the molecules will come into contact when they do. If we look at this mixture here where we have carbon monoxide and oxygen, here we've got another oxygen molecule. If we get oxygen colliding to oxygen here, there's no reaction going to occur. Okay, so that doesn't have the right orientation. It has the wrong orientation. Okay, in order for this reaction to occur, we want a reaction to occur between carbon and oxygen. So the carbon and the oxygen need to collide in order for the reaction to occur. So carbon to carbon, okay, or carbon to oxygen. We need to have this carbon to oxygen in order for us to make CO2. Okay, so in this case, the molecules will collide randomly. Sometimes they'll have the right orientation, sometimes they won't. If a reaction is going to occur, the first thing that has to happen is they need to have the right orientation. Okay, and we refer to this as setting up for a successful collision. Okay, this is a fruitful collision. It results in the formation of products. It's fruitful. But of course, we said not only do they have to have the right orientation, they also have to have the right amount of energy. Both things have to be met in order for the reaction to occur. So when we talk about energy, two things can collide with the correct orientation, as this one here. Orientation is good, but if they just sort of bump softly into each other, there's going to be no reaction. They'll just sort of collide, bounce off each other, and we won't see a reaction occurring. Okay, no reaction. What we need, correct orientation, and we need them to be slamming into each other with enough energy that these bonds are going to break so that we can form new products. Okay, in this case, we have correct orientation and energy is also good, so we get a successful collision. So converting the reactants to products requires the particles to collide with sufficient energy to break the bonds between them, which allows the formation of new products. Okay, without that much energy, we're going to have no reaction. So what we've really got to look at is, well, how much is enough energy? And if you remember back to the energy level diagrams we were talking about with endothermic and exothermic, okay, reactants here, products there, this is actually an exothermic profile. Okay, get used to identifying these as you see them. Then we know that bond breaking is as we go up the hill. So this energy from the top of the hill to where our reactants are is going to be our activation energy. And that is the energy that is enough to break those bonds and get the reaction going. Okay, so the highest point on the energy profile diagram to where our reactant started from is our activation energy. That is the minimum amount of energy that we need to put in order to break the bonds in the reactants and get the reaction starting. So we need to have a collision that has the right orientation and meets this minimum energy requirement, okay, in order to proceed. Okay, so this one here, once that happens, then the rest of the reaction will occur and we will have the formation of new products. Okay, so make sure that you've noted down the minimum energy of, to get the minimum amount of energy to get a reaction going is known as the activation energy. We give it a capital E and a subscript A to show that that's energy of activation, A for activation. So if we revisit our energy profile diagrams that we looked at for exothermic and endothermic, we can see that now we have energy on the y-axis, reaction progress on the x-axis. We have our reactants and our products. The big hill, okay, up to the top here, the difference between the two is my activation energy shown by the blue arrow here. And then in this case, this is an exothermic reaction. So the difference between the reactants and the products is how much energy will be released. In an endothermic reaction, the reactants are lower than the products. It's a much bigger hill to get up, so we actually generally see greater activation energy being required for an endothermic reaction. Okay, so typically an exothermic reaction will have a lower activation energy than an endothermic reaction. Okay, and then remembering that the energy absorbed is going to be from the product to the reactants. Make sure that you have sketched each one of these as an example so you know how to draw them. This is a skill that you need to have to move on and be able to do in your assessment items and explain the difference in activation energy between exothermic and endothermic reactions. So that's it from me. We will have a look at this other video when we're in class. So make sure that you have your notes complete and then you can go on to completing these activities here. Okay, so I'll see you in class.